today, so we're gonna talk about the basic of Gaussian, and we'll briefly talk about the geometry optimization using Gaussian. For that, so we're going to review some concepts in quantum chemistry, and also the concept of Hartree-Fock calculation and density functional theory, and based on that, and after that, so we will briefly talk about how to run Gaussian and what is geometry optimization. So here's the title. So today we're going to talk about, first time we're going to talk about Hartree-Fock method and what is Hartree-Fock, and we'll also take a look at what is the concept of molecular orbital, and we're going to talk about the geometry optimization and about running Gaussian. So yeah, we'll briefly review what we have talked about in the last class. And so as we talked before, so usually, so since we're studying chemistry, so the subject of chemistry are molecules. So we deal with molecules, and molecule can be defined as a multi-electron system. So the main characteristic of molecule is that so it consists of many atoms which contain many electrons. So we have to deal with the properties of many electrons, but as we have discussed before, solving the Schrödinger equation of multi-electron, many electron is not easy. So we generally approximate the wave function of multi-electron system as a product of individual electrons. So here, so we generally ignore the correlations between electrons. So how can we how can we build the molecular orbital of a molecule? So the molecule is as I mentioned, so the molecule is a system that multiple atoms are connected by covalent bonds. So in order to obtain an approximate wave function, so because we cannot write down the exact wave function of a molecule, so we use an approximation. So we use an approximation called LCAO model. So the LCAO means linear combination of atomic orbital. So the linear combination is what? So linear combination means, so these are the atomic orbitals which can be solved rather easily, but so then we combine them by adding them or subtracting them. And so the linear combination means that we multiply something and we just add. So we multiply constants. So these are numbers, not other functions. So these are numbers and plus, and we do adding, addition, or subtraction. So that is linear combination. So for example, so we represent the wave function of a water molecule as a sum of these three atoms, because water consists of two hydrogens and one oxygen. So this is the one example of the LCAO representation of the water molecule. And we also talked about the variation of principle. So variation of principle means that, so if we know the true wave function, then we can get the true energy of a system. So here the E0 means the true energy, right? So in principle, by calculating this property, by calculating this equation, then we can get the true wave function of a ground state of a system. But as we discussed, since in general, so we don't know the true wave function of a system, so we have to write down, we have to use an approximate solution. So if we assume that this phi is an approximate wave function, then we can get approximate energy by solving this equation, right? But the variation of principle means that, so the important result of variation of principle is that approximate energy of a system is always greater than true energy, or equal, greater or equal to the true energy. So this relationship tells us a very important hint to get a true energy. So, so if we change some parameters, so it means that, so first, we write down an approximate solution, then, we can tune it, we can refine it. So when we change some parameters in our approximate solution, then after that, so if the energy, approximate energy becomes lower, then it means that our solution became closer to the true energy and true solution. So it means that if our approximate solution is very close, very similar to the true solution, then the energy value will be also very similar. But it never gets lower than the true energy. So it means that so if we change some parameters in our approximate solution, then after that, so if energy becomes lower, then it means that so we are getting better. But at some point, so after several refinements, so the approximate energy will not be lower, because if it reaches to the true energy, then it cannot be lower anymore. So by using this, so we can get an approximate energy quite accurately by using this relationship, right? So 그래서 아마 이거 좀 오케이. So 이게 아마 어려울 수 있을 텐데, 그러니까 이제 오케이. 그래서 이제 우리가 어떤 이제 true wave function이 있는데 얘를 우리가 잘 모른단 말이지. So we don't know this true energy. So so we use approximate solution. So this is the 이건 이제 근사치야. 그래서 우리가 이제 얘가 요거랑 비슷하다고 생각을 하고 이제 뭐 exponential minus a1 r 뭐 이런 식으로 쓸 수가 있어요. We can write down like this. 근데 이제 우리가 처음에는 얘네들을 처음에는 대충 근사를 했다가 이제 그 뒤에 나오겠지만은 이제 계산을 하면서 요 값들을 우리가 계속 바꿔볼 수가 있단 말이에요. 계속 바꿨는데 we can change these parameters. But 그럼 얘네들이 잘 되고 있는지 안 되고 있는지를 우리가 이제 어떻게 아느냐? 그러니까 뭐냐면은 근사값은 그러니까 얘네들을 이용을 해서 우리가 이제 에너지를 계산을 할 수가 있는데 요거로부터 에너지가 어떤 true 값보다 변분법에서 얘기하는 중요한 의미는 뭐냐면 approximate energy never gets lower than true energy. 그러니까 이제 true energy가 있으면은 근사 에너지, 요걸로 얻는 에너지는 어떤 값 이하로는 절대 떨어지지 않는다는 거예요. 그러니까 이제 우리가 뭐냐면은 우리가 이제 처음에는 대충 근사를 했다가 나중에 점점 얘네들을 이제 이렇게 좀 이렇게 이제 고칠 수가 있잖아요. 점점 더 정확하게 바꿀 수가 있는데 그러면 as solution gets more accurate. 그러니까 이제 솔루션이 점점 더 이제 진짜 값에 more accurate 해줄수록 에너지는 점점 내려간다는 거예요. 그러니까 이제 뭐냐면 우리가 어떤 숫자를 하나 바꿨는데 그럼 얘가 잘 바꾼 건지 좋은 건지 나쁜 건지 어떻게 아느냐? 그럼 바꾼 다음에 에너지를 계산을 했을 때 그 전거보다 에너지가 내려갔다. 그러면은 일단 좋아졌다 우리가 생각을 하는 거예요. 그래서 이제 그러다가 어느 순간에는 이제 아무리 바꿔도 에너지가 더 이상 낮아지지 않겠죠. 그러니까 그 순간에는 만약에 우리가 정말로 true solution의 근처에 왔다면은 어차피 더 이상 내려갈 수가 없기 때문에 그래서 이제 계속 바꾸다가 이제 더 이상 안 내려가는 데쯤 이제 스톱한다는 거예요. So that's the key point of variation principle. So that was the review of the materials what we covered last class. And so today we're going to talk about the Hartree-Fock calculation. So the Hartree-Fock calculation is the standard way of calculating energies of molecules in computational chemistry. So Hartree-Fock is one of the most widely used method, and this is one of the basics of computational chemistry. And then let's look at the basic concept. I mean, what does the Hartree-Fock calculation mean? So as we talked before, I mean, so we have to generally, I mean, we have to calculate the energy of multiple electrons. I mean, so, but solving the Schrödinger equation of multiple electrons is difficult. So instead of solving the Schrödinger equation of multi-electrons at the same time, so we solve the equation of, we only solve the Schrödinger equation of one electron instead of solving multiples at a time. So which means that so when we have a water molecule, how many electrons does it have? So it has, this one has 6 electrons, and this one has 1 and 1, and so there are 8 electrons in total, right? So there are 8 electrons. So in principle, I mean, so we have to solve the equation consists of 8 variables. So in principle, we have to solve the equation of 8 variables, but this is too hard to solve. So instead, I mean, so how do we solve it? So in Hartree-Fock calculation, we assume that, I mean, so we are interested in only one electron at a time. And what about the rest of the 7 electrons? And we assume that other 7 electrons are just dispersed, spread over the space. So we assume that 7 electrons are just considered as cloud, so they are all spread all over the molecule. So by doing this, I mean, so we can only solve the equation of this one, right? So then, I mean, so we can only solve, I mean, the Schrödinger equation of, so here, so let's assume that, so we are solving the Schrödinger equation of electron number 1, so let's assume that this is electron number 1. And here the EFF means effective potential. Effective potential means, so it means that electron number 2, from electron number 2 to number 8 are just, I mean, included here. So we're just, I mean, including them as a cloud. I mean, they're spread over. So. And this becomes the energy of electron number 1, and we solve the wave function of electron number 1. Then, okay, by doing this, I mean, so we can, I mean, this is much easier than solving, I mean, equation with 8 variables, right? I mean, so after solving this, and we solve this, then what about, I mean, electron number 2? Let's assume that electron number 2 was here. Then, I mean, so we can just, I mean, we just, I mean, now this time, I mean, so we assume that electron number 1 is also dispersed, spread over a molecule. Then, I mean, we solve the equation of electron number 2. So after that, I mean, so we solve the equation of electron number 2, and after that, I mean, so we again, I mean, assume that electron number 2 is spread over the molecule, and we solve the equation of electron number 3. So by doing this, I mean, so we can solve the equation of each atom, right? I mean, so by solving, I mean, 8 separate, I mean, Schrödinger equations. So as I mentioned here, the effective potential is that, I mean, the potential that, I mean, this electron experiences because of nuclei, and this electron gas, I mean, electron cloud. So, I mean, let's assume that, I mean, if electron is here, then usually, I mean, so if there's no electron, then, I mean, so it is attracted by this 6+ nucleus, right? But, I mean, since we are assuming that other electrons are all spread over here. So, so the negatively charged cloud is, surrounding these nuclei. So, so this one will experience less attractive potential. And because of this, there are some, repulsive interaction between this cloud and this electron, right? So the effect of all the other electrons are considered here. So this is the Hartree-Fock approximation. So this is the called one electron approximation. So in summary, so Hartree-Fock calculation means that so we solve one electrons at a time, right? And we do this iteratively, right? We do this. So we do this iteratively, right? You know this word, right? Yeah. So iterative means keep doing it to repeat. So this kind of process is also, yeah. So as you mentioned before, so as I wrote before, so usually in Hartree-Fock calculations, so the wave function of each electron is approximated like this. Here the Ci and Ni's are constants, so they should be determined, they should be refined. So, and here the zeta I, so this is called zeta, so this is a Greek alphabet, and this zeta is called as effective nuclear charge, the effective nuclear charge. So these equations are, I brought them from, I adapted them from the textbook. So if you don't remember these, so you can check the textbook. The physical chemistry textbook. Right? So these are constants, and this is the effective nuclear charge. Effective nuclear charge means that, as I told you before, so at the vacuum, if electron is here and oxygen. So let's assume that this is oxygen, and oxygen, the nucleus of oxygen has 6 plus, and so it should be attracted by minus 4 pi epsilon r over 6 e n. But in reality, or by using Hartree-Fock approximation, because so this is surrounded by negative cloud, so this nucleus charge will be lower than 6, right? So that is effective nuclear charge. So effective nuclear charge is here, and this R is distance between nucleus and electron, and this A0 is the Bohr radius. So here, so we have to determine these numbers, these numbers, and they are represented as sum of m terms, right? So I explained about this plot, right? So here this blue line, this red line is the true orbital, and this blue line is an approximate solution. And our goal is to find the right numbers, to find proper numbers that make this blue line is as similar as this red curve, right? So we have to determine these parameters. If we find the right parameters, then we can get, very close, very good approximations, then we can get very good approximate energy, right? So the Hartree-Fock calculation is iterative, as I mentioned, and iterative process is often called self-consistent field calculation. So the self-consistent. So self-consistent means that, so as I mentioned, as I explained, so we, for water molecules, so we solve 8 Schrödinger equations. After that, so we can solve this Schrödinger equation of this electron number 1 again, right, based on our previous calculations. After solving that, so if parameters, if energy or some other numbers change, then we we repeat solving these Schrödinger equations again. And we repeat this, we iterate this on and on and on until the numbers, until the energy doesn't change. So it means that so we start from the initial gas. So the first gas. So we start from some gas. Oh, so these numbers should, for example, so here the C1 should be about 0.1 and N1 should be about 0.2. So we start from the gas, but we solve on an 8 Schrödinger equations, and we keep doing that. And so first we solve Schrödinger equation, then if each electron iteratively, and so one by one, so here the 8 times, then check, how much energy and parameters are changed. So we solve this one, and after that, we solve the Schrödinger equation of electron number 1 again, and if energy changes a lot, then we solve them again. And after that, we solve the Schrödinger equation of electron number 1 again, and if energy change is small means that, so these parameters, so all these parameters are quite good. So as I mentioned earlier, so if our approximate solution is here, so there isn't that much room for improvement. So it cannot be lowered that much. But if our solution, if our approximate solution was here, then after one iteration, then maybe energy can be lowered. If this delta E is large, it means that so our approximate solution is far from true energy, right? But if our approximate solution is very close to the true energy, then its energy will change small. The energy changes will be small, right? So that is written here. So if energy change is small, we stop there. So we think that the calculation is converted. Otherwise, so we go back to number 1 and we solve equations for each electron iteratively. So, so if you, so these are all written in, physical chemistry textbook. So if you are not certain about this, and so you can check out the, chapter 16 or 17 in our physical chemistry textbook. So by doing this, so we can solve the molecular orbitals. So these are the examples of molecular orbitals. So we know that so these are the p orbitals, right? So these are p orbitals. But when two p orbitals are combined, we also learn that they can form, pi orbitals, right? So in organic chemistry class, you learn that, if two p orbitals are combined in a parallelly, then so they become pi orbitals, right? So this is the form of pi orbital. So this pi orbital is not just the conceptual imagination. So actually, so they are obtained from this Hartree-Fock calculation. So if you do this mathematical procedure, then so we can show that so the bonding orbital actually looks like this. But at the same time, we can also show that so anti-bonding orbitals looks like this. There's a node. So these are the examples of molecular orbitals, and from now on, so we're going to shorten. We're going to use word MO. MO means the abbreviation of molecular orbitals, right? Acronym of molecular orbitals. Acronyms, right? So acronym means, that's what you usually likes to do. So you usually likes to shorten the words, right? So the acronym MO means molecular orbital. So here's the M and O. Okay, yeah. And there are other examples of molecular orbitals. And so if we have, and this is the example of water molecule. And so here the y-axis is energy. So these are the lower energy orbitals, and these are high energy orbitals. So let's take a look at what does this mean. So here the lowest energy orbital. So if you see, then there is a very small circle, right? So the lowest energy electron. So this means that the lowest energy electron is placed here in this green circle. So it means that when there's a water molecule, so let's assume that there's a water molecule and we have to put 8 electrons, right? And the lowest energy one is located here. I mean, this is natural, right? Because I mean, this one has 6+ nucleus. So I mean, if electrons are very close to this, and this one will have very low energy, right? Because I mean, this is attracted by nucleus very strongly. So this electron has lowest energy. But I mean, as we learned from Pauli's exclusion principle. Pauli's exclusion principle. And so we know that this orbital can have only 2 electrons, right? So there can be 2 electrons can be here. So there are 2 electrons, I mean, occupying this orbital. And the next level, so if 2 electrons go into this orbital, then that is fully occupied, I mean, there is no room. And so the next electrons should go to another orbital. So based on Huffington calculation, I mean, the second lowest energy orbital looks like this. So the third electron, if third electron comes, then it should locate like this. So because this one is more, dispersed, more spread. So this one is farther than these electrons, right? I mean, so this one will be attracted less strong, right? More weakly. So this one has higher energy than this one, and the next energy orbital looks like this. So it means that the electrons are occupying here or either here. So if you see this electron, but I mean this one will, the third and fourth electrons will occupy here, and the next orbital looks like this. What does that mean? I mean, so the electrons are playing around here or playing around here. So if you take a look at this, I mean, then actually it means that electrons are playing in between, are placed between oxygen and this hydrogen. So which means that, I mean, this electron, so electrons in this orbital is kind of helping this oxygen and hydrogens are bond together, right? So these electrons are playing in between oxygen and hydrogen. And also next orbital looks like this, and next orbital looks like this, maybe. And we also learned that from the class, I mean, the terms like HOMO and LUMO. So from here, I mean, so we, maybe I should have put those words, I mean, but sorry about that. So the HOMO means, what does HOMO mean? So HOMO means highest occupied molecular orbital, right? So then, I mean, where is the HOMO here? So the HOMO is, I mean, so let's look at it. So, I mean, this water molecule has 8 electrons. So 2 electrons go to here, 2 goes to here, and 2 electrons goes to 2, what is it? Is it 2, 1, 2, 3, 4. Right. So this one becomes the west minus this one. Oh, sorry. It has 10 electrons, right? Oxygen was number 8, right? My mistake. Yeah. So I mean, it has 10 electrons, right? So I mean, so it has 2 electrons goes to here, 2 electron goes to here, 2 electron goes here, 2 goes to here, 2 go to here. So 10 electrons are occupying up to these 5 molecular orbitals, right? So the highest occupied orbital. I mean, highest energy. Occupied orbital means that so this orbital is occupied by electrons. But what about this orbital? This orbital is empty. This orbital is empty, right? I mean, because we have only 10 electrons in water molecule, and so the LUMO means lowest unoccupied molecular orbital, right? So this one becomes LUMO. Then, I mean, why should we care about, I mean, empty orbital? Because, I mean, so if we, I mean, so these are the lowest energy ones. So these are at the ground state. These are at the ground state. But if we, you know, if we put laser and, I mean, if we give some energy to this molecule, then electrons can be excited, right? I mean, electrons can get energy. So if this electron gets excited, then where does it go? I mean, so then the next letter, it usually goes to the next letter. So the electrons are playing like this, but after that, I mean, if it gets some energy from, you know, sunlight or from laser, then it is excited and it goes to this orbital. So this one is empty, but I mean, but if this one is excited, then I mean, electron moves from here to there. Okay. So in chemistry, usually, I mean, so HOMO, LUMO are important because, I mean, so the HOMO, LUMO gap between this HOMO and LUMO are the smallest energy gap to be excited. So these are the smallest energy to make, you know, a molecule excited. So these are the molecular orbital of benzene also. So the lowest energy pi orbital is that, I mean, so it is, you know, the pi orbital electrons are spread over all 6, you know, carbons, right? So this one is helping all carbons are bound together, right? And the next higher energy orbitals looks like this. But what about the highest energy orbital? At the highest energy orbital, I mean, electron is playing around the carbon atoms, right? I mean, so it is not helping them to make bond. So here, these are the orbital pictures, right? I mean, so all great things. So here, I mean, let's say that, so let's take a look at the, I mean, this example and this example. So here, the orbitals are shown like this. So this means that electrons are playing around here. So it means that electrons prefer to be playing around between this carbon and carbon, right? I mean, so this electron cloud, this orbital helps this carbon, and this carbons got bond together, right? But at the highest energy orbital, I mean, for this case, so electron clouds are all separated, right? In this case, I mean, electrons are just, staying, placed. 2 electrons are just, placed next to carbon nucleus. So it doesn't help, to make, covalent bonds, electrons should be in between, nucleus, so that, so you can attract to nucleus, right? But in the high energy orbitals, so they are just, placed around the nucleus, so they don't help to get bond formed. So this means that, so if we give some high energy to a molecule, then electron moves from here to here, then it means that, they don't like to be bonded. So if we give, high energy to a molecule, then molecules become, broken out, and they are separated, right? So by running, Gaussian calculations, so we're going to obtain these pictures actually, during the practice session. And the next one is called, so we've talked about the Hartree-Fock calculation, in short, HF calculations. But in these days, so there are different types of calculation instead of Hartree-Fock calculation. That's called density functional theory, so in short, DFT. So in DFT, so DFT calculates the energy of a molecule from the electron density. So what is electron density? Electron density is actually the square of wave function, and electron density is actually something we can see, something we can measure, instead of using a wave function. For Hartree-Fock calculations, so we use the wave functions, but in density functional theory, so we use density instead of wave function. So, the theory behind this DFT is a bit more difficult than Hartree-Fock, so we're not going to talk about that. But one thing you should remember is that the most widely used DFT method is called B3 LYP. So that is very similar to 631G basis. And if you some of you may go to grad school, and some of you will read papers, and so these days people are widely using this DFT method, and so you will see this one quite frequently. And so if you see this one, you can just think that they use just a very standard method for computational chemistry. Okay, we're going to skip this, and we'll skip this too. So actually, during the practice session on Friday, so we're going to use Gaussian, and so you're going to run Gaussian calculations by yourself. So so maybe you get a bit terrified because so all the theories behind this seems to be very complex and difficult. It must be super hard and super difficult. But but I'm going to show you that so actually running Gaussian is not that difficult. Theory is difficult, but people made it easy, so things are not that difficult in practice. So I'll just briefly give you a preview of what we are going to do on Friday. So these windows are called Gauss view. So in Gaussian, so the Gaussian is the program that actually does calculation, and Gauss view is a graphical interface so that we can run Gaussian. So most of the times you'll see these windows. So you will not see Gaussian. So Gaussian is just a program running inside this program. So it has a builder window and viewer window. So in order to run a molecule, first we have to build. We have to draw a molecule, right? So by using Gauss view, so we are going to build a molecule. And from here, so as I mentioned, so this is the graphical interface. So there are many icons, and so you're going to actually do this on Friday. And so by using these icons, and so you can draw these molecules. You can draw this molecule, and you can draw this molecule like this. And after drawing that, so you're going to do a geometry optimization. Because by using these tools, so you can draw these molecules, but they are just the initial guess. So you can draw like this, but you don't know exact length of this CC bond or something like that, right? The most common task of Gaussian is geometry optimization. So the geometry optimization means that it finds the energy minimum. So for example, so in this plot, so here the x and y point is the one conformation. So as we learned in the organic chemistry class, so one molecule can have multiple structures, right? All those structures have different energies. So usually, we are interested in low energy structure, low energy conformation, because high energy conflations are unstable. So usually high energy conflations disappear very quickly, and usually so they exist, molecules exist as their low energy conformation, right? So as you learned from our calculus class, our math class, so generally, so there can be many, many minima, right? So many minima, but some of them are called local minima, but some of them are called global minimum. So global minimum means that, so this one is minimum, locally minimum, but maybe when you have a graph like this, we know that so these points are minima. Minima is in Korean. But these all three are minima. But the global minimum here, what do you mean? Global minimum is that the lowest, only one, the lowest energy of all range. So the global minimum is here because so among these three, so this one has the lowest energy, right? So then what other two, and these two are called local minimum. Okay? Because locally this is minimum. But if we go over these, then this one has lower energy, and this is the lowest possible energy. So this one is generally called global minimum, and we are mostly, in many cases, we are interested in global minimum. So we have to find the right confirmation. So let's take a look at the example. So let's take a look at the example of ethane. So we can draw this ethane by using Gaussian view. So you're going to do that on Friday. And here we know that this angle is rotatable, right? So this angle is called dihedral angle, and we can rotate them. We can rotate it, right? So by modifying, by changing dihedral angle, and we can set its angle. So we can set the angle between 1, 2, 3, 4 atoms by changing this slide. And so let's assume that so we set the angle as a 60 degree. Then if we look at the ethane from the front, then it will look like this, right? But if we set the angle between if we set this dihedral angle as 90 degree, then it will look like this from the front, right? Then which one will have lower energy? This one will have lower energy, right? So you've already learned it, right? So so geometry optimization means that if you start from this conflation, then we know that this is not stable. So actually this is stable, right? So starting from here, finding this confirmation is geometry optimization. Okay? So so since we're going to do this on Friday, so I'll skip here. So if you do calculation, then if you calculate the energy of this confirmation, then here, if you run calculation, then there's a Gaussian gives you the energy of this structure. So energy is written as minus 78.76, blah, blah, blah. And here the AU means atomic unit, right? So in quantum chemistry, 1 AU is called 1 Hartree. So 1 Hartree is an energy unit. So 1 Hartree corresponds to, 1 Hartree is 627.509 kilocal per mole. So that is very large energy. So the initial confirmation is minus 78.7, blah, blah. But if we do geometry optimization, so we know that this is unstable, right? So if you do geometry optimization, then Gaussian modifies, changes structure like this because this one is stable, right? And Gaussian gives us the energy of this structure. Energy is minus 78.7939. So if you see that, there's a small difference, right? And the energy difference is actually minus 0.0079 or 615 atomic unit. So this seems to be a very small number, but actually, so if you multiply this number, then the energy difference is about 5 kilocalorie per mole, right? So the 5 kcal per mole is a bit of energy, right? So it is not that small, so it's something that can happen at room temperature. So we're going to do this, so on Friday, and actually, so running Gaussian is actually might be easier than the running proteins. So this is what we are going to do on Friday, and okay, so this is the just for the day, and